Afternoon. In this talk, we'll be examining what can be learned about active faulting and other processes based upon normalized channel steepness index within the state of Utah. Utah has three different physiographic provinces, including the actively extending basin and range, the Colorado Plateau, which is much more stable, not experiencing major active extension, but has experienced kind of epiorogenic uplift over the recent geologic past. And then in between the transition zone, which is a zone of normal faulting as well as like the basin range, but just has less well-developed basins. To the north of the Colorado Plateau, there's also the east-west oriented Uinta Mountains, which are part of the Rocky Mountains. So I got involved in this project along with my students, Parker Farnworth and Veronica Richards, who are now graduated and working as professional geologists, because we were studying active faults in Utah from a paleoseismic standpoint, looking at their recent kind of Holocene activity and comparing major faults such as the Wasatch, which is our most actively uplifting fault zone in Utah over the late Pleistocene to present at 1 to 2 millimeters per year of uplift, as compared to many of the other faults in Utah, which you all see, if you look at them, are all slipping at orders of magnitude, 1 or 2 orders of magnitude less vertical slip with time. So I wanted to see how KSN and tectonic geomorphology maybe reflects those differences or not. Given that tectonic geomorphic metrics such as KSN are kind of sampling timescales longer than the Holocene, going back into kind of millions of year timescales. Okay, so briefly, let's look at our methods as an overview. So KSN, it comes out of a product of looking at the relationship between slope and area on a log-log scale of river drainages. So if we all know that rivers have these concave up profiles. If we look at a segment of that river, we measure its slope and its upstream drainage area, and then plot it amongst all the other river segments in a system, we see that they would form a nice kind of relationship like we see in these plots here. And the relationship of this on this log-log scale is that slope equals area times a constant, that steepness index, or KSN, raised to power, which is the trend in that line, and we refer to that as concavity. And so if we use a reference concavity, and it's been shown by many studies that 0.45 is a pretty universally accepted reference concavity, even though it might vary from place to place. If we use a similar reference concavity, we can compare these steepness indexes and see their relative steepness normalized per drainage area. And so we know what the area is, we know what the slope is, we apply a reference concavity, we can get at KSN for any segment of the river. So to do this, we used the ALOS World 3D digital elevation model, clipped to the state of Utah in NAD 83 UTM zone 12N with 30-meter pixels. We extracted only the upland parts of the state using a random forest classification, so that we were not looking at distributary networks and playas, but only mountains. And then we also did not look at any river channels that extend beyond the state, because then we wouldn't have the area upstream. To do the analysis, we used MATLAB, Topol Toolbox, and TAC. And we calculated normalized channel steepness index, KSN, as well as KSNQ normalized for discharge, with some assumptions about long-term rainfall using PRISM data from Oregon State University. And ultimately, we look at the results spatially across the state to study differences based upon fault slip rates, active and passive sides of ranges, rock strength, and any other anomalies we see. So here are the basic results. In all the images we're moving forward throughout the talk, we're going to see the same color scheme where high KSN values are shown in yellow, kind of middle is in magenta, and low values in blue and black. We see that the highest KSN values on the western half of the state are associated with the active mountain fronts that were known to be active from late Quaternary fault studies, such as the Wasatch, East Cache, Ochre, and Stansbury Mountain faults. So not a big surprise there. There were some surprisingly high KSN values, including the Raft River Range, Deep Creeks, and the Wasatch Plateau, and we'll look at those briefly going forward. On the east side of the state, we see high KSN values on the south side of the Uintas, and we won't look at that otherwise in other slides of the talk, but this is probably due to recent glaciation and steepness of those channels, as well as drainage integration across the Colorado Plateau as those channels flow into the Green River. We will look briefly at Desolation Canyon along the Green River and the tributaries, which have high KSN values there. And we also see high KSN values along some of the tributaries of the Colorado River and isolated peaks on the Colorado Plateau. Here, we're just looking along the Wasatch Front. The northern portion of the Wasatch Front is shown on the left and the southern on the right. And we see that the Wasatch Fault's main segments really stand out with high KSN values. We also see that the mountains just to the west, other basin and range, normal faults lead to much less steep river channels, showing their less activity through time. And we see that the front side of the range, the more active side of the range, like we see along the Weber segment here, is much more reflective of high KSN values than the backside of the range, showing us that there's greater uplift as we move towards the fault. In this image, we're again looking at the main segments of the Wasatch Fault and moving towards the kind of less active segments to the north and south. But we're looking not only in kind of the individual river channels, but we're now summing up average KSN values across entire fault segments as shown in the tables, and for individual river basins along the fault, the Wasatch Fault. And so what we see is that for the 5 main segments of the Wasatch Fault, KSN values range from 100 to 150, but there is some heterogeneity as we move through the different drainage networks, where if we look at, for instance, the Salt Lake segment, the drainage networks to the south side are higher KSN values than to the north side. And this is probably reflective somewhat of rock strength, where on the lower image we see weaker rocks are corresponding to those lower KSN values in those river channels, and stronger rocks, higher KSN values. And we can see that just looking at the mountain front as well. Areas on the left there are corresponding to those weak rock mountains, and areas on the right to the strong rock mountains. But there may be feedbacks, right? You have stronger rocks. Those areas have also reached higher levels. They have greater incision by glaciers. And so there may be some feedbacks that are real in terms of uplift as well. Moving forward, so asymmetry of channel steepness, we looked at this across select horsed ranges in the basin range. So we are looking at the Ochre, Stansbury, and House ranges, as well as the Deep Creeks. And here, all of these mountains have faults or quaternary faulting on both sides of the range, but there is one side that has more faulting. And when we look at KSN, we see that those same sides of the range that had greater numbers of fault scarps and greater heights of fault scarps also have greater KSN values. This shows us that there's a persistence of this asymmetry of faulting on these ranges over much longer time periods than the late Pleistocene, over millions of millions of years of time, as reflected by KSN. So let's move forward to another anomaly, and that shows us again that rock strength is really important. So here we're looking at the Raft River Range, way up in northwestern Utah, and here there's kind of uniformly high KSN values all around the mountain, and that's because it's uniformly hard rock all around the mountain. So we're looking at the exposed metamorphic rocks of a core complex shown here. Another anomaly we saw was the Wasatch Plateau and monocline, which is running kind of north-south in these images. Right here is this monoclinal axis. That's not a fault. There are faults, normal faults just to the right of it in small little fault grabens. But we see the highest KSN values here just to the west of the monoclinal axis. And we also see, when pulling up LiDAR in the center image, a great steep slope break there. And then if you look at the geologic map of this area, we see some evidence of faulting in the long-term geologic history. But this LiDAR image and this steepness index kind of tells us that this fault zone seems to be active over the Quaternary and probably deserves further investigation for seismic hazard analysis. And then finally, moving on to the Colorado Plateau, we see that high areas of KSN include the isolated igneous cored laccolith peaks of the La Salles, Abajos, and Henry Mountains. And those are like this because there's been this long-term broad uplift of the Colorado Plateau. Thousands of meters of sedimentary rock have been stripped away, exposing these hard rocks in contrast of these mountain ranges and preserving those steep channels. Additionally, moving to the left, and maybe quite an interesting story, we're looking here at Desolation Canyon along the Green River, which is flowing to the south in the image on the left. And other studies have shown that there's a major contrast in erosion rates downstream and upstream of Desolation Canyon, and this big broad nick zone as Desolation Canyon and the Green River cuts through the Book Cliffs escarpment here. So downstream we see uplift or incision rates that equilibrate to about 450 meters per million years, which is an order of magnitude higher than the upstream rates. And so all these high KSN values that we're seeing on these side tributaries of Desolation Canyon, we believe are related to the really recent history of this drainage integration of the Green River across this escarpment. And if you look at the channels that are coming in and towards the Green River, they're actually all flowing broadly to the north. And so it just kind of has this pattern of kind of drainage reversal. And so it's a kind of interesting story of drainage integration and incision that's still actively ongoing, and so must be pretty recent within the million of years to hundreds of thousands of year period. And so we'll stop the talk there for time, but just generally speaking, applying KSN broadly across an entire state like this, across multiple geomorphic provinces, we can see interesting stories of long-term fault activity in the basin and range, stories of drainage integrations, drainage reversals, and kind of broad uplift and response of landscapes within the Colorado Plateau. And so thank you for your attention.